visitors from overseas and the speakers to thank the NCTS and University of Taiwan for the wonderful host for this event. And also the staff, we have been wonderful organization. We had about 10 days of mini course already. And so I'm sure we'll enjoy the activities here and also the visitors. So thank the NCTS and the staff and the local organizers of Bellum. So thank you. Yeah. Oh, all right. Okay, then we'll start today, the first day of activities. And our first talk today will be Professor Tan from Chinese University of Hong Kong, and he'll speak on the existence and curvature estimate of Ricci. Thank you.
Close. I would like to thank the organizer, etc., for inviting me for this nice workshop. So today I'm going to talk something which are one of the basic in Ricci flow. So, but in the area of without the assumption that the curvature being bounded. That's it. Right. So this is well-known equation for Ricci flow. And in our talk, we always assume everything is smooth and complete. And if G0 initial data and GT are scalar, both scalar, we just say that this is a solution for the scalar Ricci flow. So the first is about the existence of scalar Ricci flow. So we skip the very difficult problem about existence of Ricci flow. So, before I go on, I should mention that Topping has done many things in the complex dimension 1. So we just go on to talk about complex dimension at least 2. So, as I mentioned before, we would like to get some existence result for the Ricci flow without the assumption that the manifold has bounded curvature. So let us assume M and G0 be a complete non-compact Riemannian manifold, and G0 has a non-negative compact sectional curvature, and the volume has some lower bound. Then by Wilkin and the other guy, I don't know how to pronounce his name. So then we have a short time existence. Also, GT has non-negative compact sectional curvature, and the curvature is bounded by C over T. That is the property that we will use later. Of course, in their work, they do not have to assume that the volume is bounded below. So the volume is bounded below. If without this assumption, then we still have a complete solution. However, we do not have this kind of curvature bound. Okay. So, but we only concentrate on this one because I don't know how to handle the general case. So complex sectional curvature being non-negative means that you take the complexified tangent bundle and sectional curvature carry over to the complexified tangent bundle, satisfy this kind of property. So another result is by Miles Simons. He proved that. So there exists a epsilon depending on the dimension. So that if M is a complete Riemannian manifold, we don't assume the manifold has bounded curvature. However, we have another metric with bounded curvature, so that the G0 and H are very close in the C0 norm, in C0 sense. Then we still have a Ricci flow solution for short time solution. For short time solution, for some T, and the curvature also has this kind of bounded. Moreover, the C and the T depends only on the dimension and the H, the background metric. So later on, Su also obtained this kind of result. So suppose we have a certain kind of Sobolev inequality, and the curvature is bounded in terms of LP norm locally. Then we have some solution for short time. And then the curvature also bounded by this one. Notice that because he assumed the P naught is big enough so that M over 2 P naught is less than 1. So this is T to the power minus something, which is less than 1. So even better. Recently, in the web he Perfect. He proved that suppose we have a non-negative Ricci curvature. So suppose for some fixed R naught, the isoperimetric inequality, the constant is close to the Euclidean 1. Then the Ricci folds with initial data G naught has some finite time solution, and the curvature also satisfies this condition. Okay? But of course, this condition, non-negative Ricci curvature, can be relaxed so that the Ricci curvature is bounded below by something which is almost like quadratic. Okay? So using his idea, we can also consider another case. But we have to assume lower bound of sectional curvature. But the isoperimetric inequality can be replaced by this one. So in his case, he just used the pseudo-local theorem of Perelman. What we did is to use a pseudo-local theorem by Tan and Wang. So of course we can just construct Kähler-Ricci flow under certain kind of condition, all right, already. But the conditions are not very good, So anyway, so that is the question we would like to ask. Suppose GT is a complete solution to the Ricci flow. Suppose G0 is scalar. Whether GT is scalar or not. So we would try to discuss this question. Another question which is also interesting in complex geometry is that suppose we have a Kähler-Ricci flow already, and the G0 has non-negative bisectional curvature. How about when T is bigger than 0? So as it is well known, if everything is compact or has uniformly bounded curvature, then the solutions are well known, all right? Both are true. So if initially it's scalar, then when T is bigger than 0, it's scalar. If it's non-negative bisectional curvature, when T is bigger than 0, we also have non-negative bisectional curvature. So that is the well-known result. So now one can show that under in the previous example, suppose we have a Ricci flow so that the curvature satisfies this condition. Then if G0 is scalar, then GT is also scalar. So that is the first result. So maybe we just call this about an answer on the existence of Kähler-Ricci flow. So under certain conditions, we have Kähler-Ricci flow. So we sketch the proof. The proof is rather standard. First, we just take the complexify tangent bundle, decompose into one CU or one part, and then using the Ehrenberg trick, and then take a fixed vector bundle, and then U0 is an isomorphism, and then evolve U0, and then pull back the curvature to get another curvature R tilted, all right? It basically satisfies the same kind of property. So, and then take the metric. This is still Hermitian at least. So then we define this one. This is just come from the result by Xiwan Shun. So we just look at this function. This function is well defined. In a unitary frame, then we have this part. So if the metric is scalar, then this should be 0. Conversely, suppose this is 0, then we know that this should be clear. We just prove it. So the main point is how to prove that phi is identical to 0. So let us look at the properties of phi. First of all, because of the curvature assumption, the curvature is bounded above by C over T. Therefore, you look at the evolution equation of the curvature, then we have this differential inequality. And then phi is less than or equal to a squared equal to t squared. Because phi is basically the curvature squared, so t squared. So we have these two properties. Okay? This is okay. But the new thing is about this one. When t equals 0, we try to compute the derivative at time equal to 0 if we assume the metric is smooth. Okay? We just prove that this one is 0. So in order to prove this, what we need is to prove that this one is 0 for all k bigger than or equal to 0. So in order to prove that, we just write down the equation. Write down the equation, you look at the right-hand side. When t equals 0, because it's scalar, then this term is 0, say for example. This term, because this is Hermitian metric, then this term is also 0, etc., etc. So what we have to do to see is what is going on for the first term. For the first term, we just write down the covariant derivative, okay? The covariant derivative is involving the critical symbol, the connection. Because it's scalar, then there are many 0 again. So we have 0 here, then we also have 0 here. Therefore, the first derivative is 0. Once we get the first derivative is 0, then we just use induction. Because when you differentiate the equation for the curvature, then you have differentiate the metric, differentiate the connection, etc., etc. So we just decompose into several propositions. The first one, the curvature, the derivative is 0. The second one, the metric is 0. The third one, the Ricci, the derivative is 0. The fourth one, the connection, and then the covariant derivative and the covariant derivative again. And then finally, we have this one, okay? So we just mix up all the propositions and then mix up, and then using induction, we have this statement which are true. So therefore, we have such kind of property. First, it satisfies this inequality. Secondly, it grows at most t to the power square, 1 over t to the power square. Thirdly, it satisfies this condition. Okay? So therefore, we need another property. So which say that suppose we have a complete non-compact Riemannian manifold, we have a Ricci fold, and for this Ricci fold, the curvature satisfies this condition. And f is a non-negative function, satisfy this kind of differential equality, and the derivative is 0 for all time t, for all k, and then the growth is at most t to the power minus L for some L. Then we conclude that f must be 0 everywhere. So using this inequality property, then we can prove that phi is identically 0, and then gt is scalar. That is the idea. So here we just use the differential inequality for the distant function by Perelman and other people. Okay. So to get this. So next, we want to talk about how about suppose the initial data for a Kähler-Ricci fold has non-negative bisectional curvature. How about when t is bigger than 0? So we can prove that this is true if the curvature is bounded by a over t, where a is small enough, depending on n. However, in our previous example for the existence of the Ricci flow, so the curvature may be bounded by some constant over C, but the constant may not be small. So therefore, we would like to remove the condition that A being small. So actually, we can prove the following. So for any A0 bigger than 0, this is not very important. And theta is from 0 to 2. And beta is anything between theta minus 1 and 1. This constant is not very important. Anyway, it's a positive constant. We can assume this is a positive constant. Anyway, theta is less than 2. Then we have certain kind of assumption. Suppose initially the bisectional curvature is non-negative. Forget this kind of local property. And secondly, the curvature is bounded above by some constant times t to the power minus theta. So theta can be minus 1.5, say for example, is more than 1. So A over t minus 1, of course, satisfies this condition. And A is just some fixed constant here. Then we can show that the bisectional curvature, when t bigger than 0, is bigger than or equal to the right-hand side. This R is just some local property, okay? So this local version will be useful later. But for the time being, let us forget this R, okay? Forget this R. So we have this one. So, and also, we have some time interval here. Some time interval here. This time interval depending only on certain kind of constant, okay? So, because of this fact, all right, suppose initially everywhere is non-negative bisectional curvature, then you can let R go to infinity, fix T. Then we have, sorry, I forgot to mention, bisectional curvature bigger than or equal to K means that this one is true. So anyway, let R go to infinity, then we can conclude that if the curvature is bounded above by t to some power minus theta, where theta is less than 2, then GT should have non-negative bisectional curvature. Okay, so that is the result we got. So on the other hand, it was proved by Yang and Zhengfeng Yang. They proved that suppose initially we have a Taylor-Ricci flow with non-negative bisectional curvature. Suppose the solution is also complete. However, they assume that this is UN invariant on Cn. So then, without any assumption on the curvature, bound on the curvature, they prove that when t bigger than 0, it still has non-negative bisectional curvature. However, we have certain kind of symmetry. So, and Chen and Jiang, Chen Binglong and Jiang and Xu, they prove the following similar thing. But for real case, if dimension is 3, if the Ricci curvature is non-negative, then Ricci is bigger than 0, without any curvature assumption. Again, we just assume it's complete. Of course, they also get the other result. It's more refined. I just state more easy to. The statement is more easy to state. So, okay. So let us go back to the sketch of the proof. The reason in the proof that the origin proof that we assume the A over T being smooth, A being small, is the following. If the bisectional curvature is non-negative initially, then at each point, near t bigger t equal to 0, then the bisectional curvature should be non-negative up to order t, right? So initially it's non-negative. The next term is t. You take the Taylor expansion, so it's only t. So, however, if we can improve this kind of estimate, then we can get a better result. So therefore, we just get this estimate. So suppose Mn is a complete solution and then this is bisectional curvature is non-negative, and curvature is bounded above by E. Bounded above by E, maybe A over T. So why we assume this? Because if we assume the curvature is, the Ricci flow is smooth, then initially for some small t, locally, of course, this is bounded. So we can always assume that. If this is true, then we have the bisectional curvature is bounded below by this one. So it's go to being non-negative in very high order, So, but this is local. So the t, we don't have any estimate for t, all right? Estimate for the t pi, okay? We don't have any estimate for the open set u, just initially. So let us sketch a Wicker result. So we assume the curvature is bounded by A over T. So the curvature is bounded is okay, but let us assume it's A over T. And we show that initially, the bisectional curvature is bounded below by minus T to the power K for any K. For any K, near T equals 0. So as before, we just introduced this tensor. We just like constant bisectional curvature, okay? And then we just take a cutoff function to do maximum principle and look at the curvature, bisectional curvature, combined with this cutoff function, and then we add something over here. B is always positive. B is always positive. We just add this part. So we add this part because initially we know that this is non-negative. Therefore, this part plus this part should be positive. Near T is 0. And then we want to get a low bound, therefore we just put a TK over here, okay? So we just take the maximum point. We just assume at the maximum point is smooth. Then we just write down everything. So just write down everything. I'll write down everything here, okay? This is okay. So we have, this term is good, positive term. This term is good, is positive term, all right? So let us look at the first term. The first term, we have to look at the lower bound of the first term. The first term just comes from the Lau vector condition. So if we go back, we look at this tensor. Certain kind of quadratic of this part should be non-negative or non-positive. I don't, maybe non-negative, okay? So this is quadratic. Therefore, we have quadratic term here, and then cross term, okay? But the quadratic term here is turned out to be negative. So we can throw it away. Therefore, we have quadratic term. You can think of phi squared and then r squared, okay? Plus phi r, all right? Something like that. Therefore, we end up with the first term will be bigger than or equal to some constant times this part, okay? K minus 1. And then, what is the second term? The second term and the third term is similar. So if you look at this third term, say for example, you just look at the maximum point, then the gradient of if psi times r should be 0. Therefore, you can replace this by if gradients if psi square over if psi and then times r, something like that. So therefore, the second term will be bounded below by something like that. This comes from the cutoff function, 1 over r. This comes from the curvature bound. And then we have to assume that phi double prime is less than or c phi. If we assume this, we should have this kind of phi, okay? Because after we do that, we can have if psi times r. But if psi times r is just equal to the run. Because, if psi times r, because if psi times r equal to 0, therefore it should be equal to this part. You just put it over there, okay? But in general, you cannot expect this one to be true, okay? You cannot find such kind of cutoff function. So we have an extra term like if psi to the power minus q, but q can be very small. So therefore, if you estimate if psi carefully, then we end up similar term like that. The fourth term look like this, and hence we have such kind of inequality, okay? Inequality. You look at the positive term, you look at the negative term. Okay, this k can be very large, okay? So k is bigger than a, then this term is bigger than this term, okay? So secondly, you look at this term, this is k minus 1/2, but this is k minus 1. This is t to the power 0 is t to the power minus 1/2. Therefore, we have some place to maneuver. That is the reason why in general, even we replace this assumption by something like that, we still get what we want. Okay, that is the reason why we have. Okay, so that is basically the proof. Okay, for this one. So in the previous theorem, we say that suppose the Taylor-Ricci flow initially has non-negative bisectional curvature, and the curvature is bounded above by t to the power minus theta. But we would like to ask whether this kind of assumption is too strong, too weak. Actually, we don't have to assume that kind of stuff. Maybe. So therefore, the next question we want to study is the following. Suppose we have a complete solution, and then what can we say about the bound on the curvature for t is bigger than 0? This kind of problem has been studied by people. So for example, they have a result, Chen Binglong and Chen Binglong Zhu, Zhang, etc. So they have very nice result in 3-dimensional, but because I don't know how to put it in a more simple way, so I just skip the statement, because what our result is motivated by the result of recent result of Simon and Topping. They obtained the following. So suppose we have a solution, 3-dimensional solution with bounded curvature when t bigger than 0, okay? And then we have certain kind of lower bound of volume. The Ricci curvature has lower bound initially. And then we can find certain kind of time interval, so that for t is bigger than 0, the volume has lower bound, and the Ricci curvature has lower bound. And the most interesting thing is for us is the curvature is also bounded by this one. All right. So that is their results. In using their method, I basically just copied their proof. Okay, so I won't go through the proof because it's not that easy. I think Mao Simon is much better, much well qualified than I am to explain. So anyway, we have this kind of result. Suppose B bisectional curvature is not negative, and the volume is bounded below, and the curvature is uniform bounded for t bigger than 0. So p bigger than 0. Then we have this kind of result. Okay, this kind of result. So according to their method, we basically need 3 things. First, for any a naught bigger than 0, for any a naught bigger than 0, if the curvature is bounded something like that on certain ball, and when t bigger than 0, the bisectional curvature is bounded below, then the bisectional curvature will be bounded below in certain kind of interval. All right? So this is just a corollary of a previous result. So initially we have if you remember, we proved that the bisectional curvature is bounded below by minus exponential of something, negative something, so it's bounded below. So the second is that suppose we have a bisectional curvature for t bigger than 0, bisectional curvature is bound, and the volume is bounded below, and then we also have this one. Here we just assume this one. Here we get this one, all right? We get this one on certain kind of interval. So in Topping and Simon's result, they use the result on three-dimensional Anson solution with non-negative Ricci curvature. In our result, we just use the result by Lee on the Anson solution of Taylor-Ricci flow. So finally, it results by Simon and Topping, some volume control for t bigger than 0, assuming initially we have some volume control, okay? So now we have 1, 2, 3, therefore we can just copy the proof and then put down what we want. So I would like to remark is the following. For the first one, let us go back for the first one. The first one, we assume that if the bisectional curvature is non-negative, then locally we have this kind of curvature. I'm sorry. If the non-negative initially is non-negative curvature, and suppose the curvature is bounded by this one, then we have some bisectional curvature for t bigger than 0. Okay. However, in their result, they assume initially the Ricci curvature is assumed only bounded below. So therefore, we would like to ask, suppose we relax the condition. Suppose the second one and the third one is okay. We don't care too much. It can be carried over very easily. But the first one, suppose instead of assuming the initial bisectional curvature is non-negative, let us assume the initial bisectional curvature is bounded below, only bounded below. Can we get the same thing? So the basic difficulty is on the first part. The first part, for that assumption, until now, we only can prove that suppose the curvature is bounded about by A over T, where A is small, depending only on M. Then we have this kind of result. So therefore, we cannot apply their theorem. Apply their method to get this one. So, okay. So that is we are still working on it. I don't know if there will be any progress. So here are some applications on the uniformization conjecture by Yao. First of all, suppose we have a non-compact Cantor manifold with non-negative bisectional curvature, complex sectional curvature, and with maximum growth. Then we can conclude that M is holomorphic to Cn. Why? Because in this case, we have a short-time existence. And then according to our result and their result, we know that when t bigger than 0, the curvature is bounded, first of all. Secondly, the complex sectional curvature is also non-negative. Therefore, the bisectional curvature is non-negative. And finally, it's not very difficult to prove that it still has maximum volume growth. Okay? And also for this, so using this kind of observation, then using a result by Chow and myself for the bounded curvature case, then we can conclude that this is biholomorphic to Cn. Also, for the His results for maximum volume growth, then we can also assume conclude that M is biholomorphic to Cn. Okay, but I have to remark that. So recently, using different methods, Gong Lao has already proved that the conjecture of Yao, under the assumption that the bisectional curvature is non-negative, maximum volume growth, but the curvature is not assumed to be anything. So he proved that we have bisectional curvature non-negative, maximum growth, non-compact, then it should be biolomorphic to CN. So I think I just finish here. Okay.
Any questions?
Yeah.
There was this interesting fact in one of the estimates where you say the, which term was it? I think it was the quadratic terms have a sign, so they fall away. But it seemed, if I was just looking at it, it seemed like the quadratic terms are going to be sort of controllable anyway because they're like epsilon times tk or something. So that squared wouldn't be too bad.
Yeah.
So somehow you get that for free, but it doesn't
You
seem
can. Maybe we have to be careful because we have t minus 1/2 term. When you take square, maybe we have t minus 1 term appear. Maybe. Originally, we don't have the tk term. We only epsilon t minus 1/2.
I thought they were just the sort of terms in front of this.
Maybe. I have to look into it. Okay.
Right.
But it certainly, if it is non-positive, it's nice.
Yeah. That's a strange fact.
Yeah.
It doesn't seem to work for the usual. If you look at the Kirbosh operator, you get the wrong sign, right?
Yeah, right. We just compare it directly, see what is going on.
I've seen the calculation. I was very surprised.
Yeah.
So in the rotational symmetric case, like
You anywhere, yeah.
is the estimate we can get here mathematically, or is it not? Suppose just
In their case, I think you let's see, if the volume is not that bad, is the volume is non-collapsing, say for example. Let us on non-collapsing means that the volume is bigger than 1. Then we just can go back to our method to get maybe when t bigger than 0, the curvature is a/t. Maybe. I have to check. Because it's, you already know that it's non-negative.
right.
When t bigger than 0, therefore we can apply them to some.
Whether they just know that
Yeah.
they can actually tell you directly without having
Yeah,
volume.
right.
Any other questions? No, well, I think Professor
Thank you.
Pemberton.
Thanks.